What I want to talk to you about today is the birth and life of stars and how we can know what we know about the stars, because they are very far away and very old, which makes them very difficult to study. And so I wanted to show you some of the science behind the theories we have for stars and star formation and the life cycle of stars. So the basic idea is we're going to start at our sun, what we know about our sun, move out, talk about stars that are farther away, and focus on stars that are similar to our sun. But then we'll also talk a little bit about stars that are much larger than our sun and how their life cycle is different than our sun's is. And we'll conclude by looking a little bit at the Milky Way. So the pictures I was showing you from the beginning are from a satellite called the Solar Dynamics Observatory. So it was launched in 2010. And its goal is to study the sun so that we can understand it more and maybe be able to predict the sun's behavior, because things like solar flares have a giant impact on our satellites and our power lines on Earth. So we want a better study of the sun for that practical application. So this satellite was rather expensive to launch. I left all my notes in my office, so the numbers are totally coming from my head. Hopefully I get them right. It's something like $250 million. It does turn out to be about $7 total per taxpayer in the United States for its lifetime, which costs us each less than $1 a year to have this satellite up there doing its research. So I have a question for you. If you held your hand at arm's length and just covered the sun, how big would you need to make your hand? Would you need your whole hand spread out to cover the sun? Your fist, 3 fingers, 1 finger? What do you think? Hold it up. I see a lot of Boy Scout pledges out there. All right, so we'll find out in a minute, but this gives us an idea. Our pinky finger is 1 arc degree. And our spread hand is about 25 degrees in the sky. And we measure things in the sky in terms of arc degrees or arc minutes because it's based on an angle is what we can see. So if you think about the sun, it is very far away. When we look at it from Earth, we see just it looks smaller than it really is, right? So when somebody's close, they're big. When they're far away, they're smaller. And you can tell this if you use your thumb to cover my head at arm's length, and then you bring it back. You don't need your whole thumb to cover my head anymore. So this idea of angular size is very important in astronomy when we're looking at things like the sun and the moon and stars. So if we do this for the sun is half of your pinky in the sky. It is half of a degree, or 30 arc minutes, and that's the same size as the moon. So if I ask you the same question as the moon, a lot of people say, well, my whole fist would take to cover the moon. But only half of your pinky at arm's length is the angular size of the moon. So we have a perception that the moon and the sun are much bigger because they're in the middle of a vast space, the whole sky. We don't have anything to compare it with. But they're actually relatively small. So it is a coincidence that the moon and the sun are the same angular size from Earth. Just a coincidence. The size of the moon is closer, but it's smaller, so it looks bigger. The sun is very large, very far away, looks smaller, happens to be almost exactly the same, which is why we get eclipses when the sun and the moon align, and the moon blocks our view of the sun. So I don't want you to think that this is the true size of the moon and the sun. So for comparison, this is part of the sun that can fit on the screen, and that's the Earth. So just for comparison, the Earth is very small. The sun is very large. We'll get a little better view of the proportions later on. All right, so what about other stars? So when you look at a star in the sky, it twinkles. It's a little dot. It's actually a pinpoint. Even in our best telescopes, almost every star is a pinpoint in that we cannot resolve it as a circle. We only have 12 stars that our best telescope can see as a circle at all. Everything else is a pinpoint because they're so far away. So the largest angular size star is one called R Doradus, and it is 0.057 arc seconds. So arc minute, 60 arc seconds. So this is much, 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 much smaller than your pinky finger at arm's length, smaller than a hair at arm's length that we're seeing here. So it takes a great telescope to look at this. The next largest one is Betelgeuse at 0.05 arc seconds. If you notice the sizes down here, Betelgeuse is 630 times the radius of the sun. But it's also very, very far away. It's 643 light years away. So it's the distance that light travels in a year, really far away. So if we look at an image of Betelgeuse, so this is the image of the star. It's in the radio wavelength. We're using a radio telescope to see it. And the black circle is what we call the optical disk. So this is what we would consider to be the star. This out here is a nebula. Betelgeuse is unstable, so it's throwing its atmosphere off. So this is a nebula that it's working on generating. So that's in radio. If we look in infrared, Betelgeuse looks a little bit different. You can see the center star and this nebula around there. And if you look with a higher resolution telescope, you can see a little more structure in that nebula, and they have blocked out the star with a black disk so it doesn't overexpose the image. So when we were first starting to learn about stars, you look up in the sky and say, where does that energy come from? What is generating the energy in the sun? So we can measure the amount of light coming out of the sun with the photometer. It's similar to photography where you measure how bright it is. You can do that with the sun. And then you can calculate how much light the sun's putting out based on how far it is away. So you can get a number for the amount of energy the sun needs to generate. And then we try to figure out where does that energy come from. Well, the Greeks thought about this and said, well, their most dense energy source ever was coal. So what if the whole sun is a big piece of coal and it's burning? That would make some energy. Well, it turns out if you have a sun-sized piece of coal and you light it on fire, it'll burn for 10,000 years, which seems like a really long time, but is not on the scale of the sun. So it wouldn't have burned long enough to power the sun if the sun was made out of coal. So a while later we had another theory. In the 1800s we said, what about gravity? As a large object contracts under the force of gravity, the molecules and atoms start running into each other and they heat up. And so that will warm it up. So as something contracts, a gas cloud contracts under gravity, it will warm up. That is a little bit better. We can get 25 million years of the energy out of the sun right now. That's closer. Would you remember how old the Earth is, radioactively dated?
About 4.5 billion.
Yeah, so if the sun was powered only by gravitational contraction, it would be dark right now. So it can't be that. Of course, we now believe that the sun is powered by fusion. So fusion reaction is a nuclear reaction where we have 4 hydrogen atoms that aren't really atoms because they've lost their electrons because it's too hot. That get smashed together and they fuse to make helium, and they give off some energy and they lose some charge too. You have 4 positive, you end up with 2 positive and some neutrons, so there's some other stuff happening, but we get a lot of energy out. So we can do fusion in the lab. We can measure the energy output per fusion reaction. We can calculate what if the sun was undergoing fusion, and we can figure out through E equals mc squared, the one equation everybody knows, right? So you take the missing mass in this equation, multiply it by the speed of light squared, you get the amount of energy that comes out, and that will work. So our sun has enough energy for about 10 billion years of fusion. The Earth is about 5 billion years old. We're about halfway through the lifetime of the sun. So this is consistent with all of the observational evidence that the sun is powered by fusion. To give you perspective, this E equals mc squared. The amount of m there that we're converting to pure energy is huge. It's about 20 Sears towers worth of mass per second to power the sun. So this is astronomical, right? You're supposed to laugh. It's funny, yeah. So lots of energy. So how can we support our hypothesis that the sun is powered by fusion? It seems like it would work. What do we know? Well, if we produce fusion in the lab, we can look at the light that comes out, and we see some patterns, and we can see some energy. If we look at the light coming out of the sun, we see something that is consistent with the fusion we see in the lab. So this is an image of the sun in, I believe, hydrogen alpha. Yep, hydrogen alpha spectrum, which is a hydrogen alpha transition, and it would be powered properly if the fuel source was fusion. So we look at the sun, and you see rainbows in the sky once in a while, right? So when we think of light, we think of the color spectrum, the visible spectrum that comes from the sun, where we take the sun's light and we split it into a rainbow. Now when we look at a rainbow, it's a nice solid band of color. No dark lines, right? When we look at the spectrum of stars, we see something a little bit different. The difference is due to our atmosphere. So this is something called a Hyades cluster. So this is a cluster of young stars. Each of these rainbows would be a dot if we didn't have a prism in front of it to make it a rainbow. And so each of these is a star with its spectrum spread out over the sky. What do you notice? So there's not a whole lot of yellow. What else do you notice?
Looks like more red.
There's a lot of red. Do all of them have the same amount of green?
You got some dark bands in there.
And you got some dark bands in there. Yeah, so we see differences, and we see some dim ones, and we see some bright ones, and we see some that are really bright in green, and we see some that are bright, farther down, or some that are bright up. That one up there is really bright in yellow. So we can see there's differences in the star spectrum. All those things give us information. If you think about it, a star is so far away, we can't go there and scoop some of it up and say, what is this? The only thing we can do to measure it is look at the light. It's our only data source for stars and anything past the Earth is light. So we're going to gather as much information as we can from this light. So some of the things that we can see, here's another spectrum that's slightly higher resolution. You see this one is very bright all over the spectrum, but there's kind of a brightest spot in there. We have some that are dimmer. We have some dark lines in the kind of light blue in some of these. Then we have some others that have, let me see if I can find one. There's a dark line right here that's a little bit harder to see in the green. Over here, there's a dark line in the purple. And so we can get data, we can get information from this. If we take our sun's light outside the atmosphere and we run it through a prism, this is what we get. Lots and lots of dark lines. When we run our sun's light through a blob of water suspended in the atmosphere, it gets all distorted and the lines get all blurred out. But if we run it very carefully through a prism, we see lots of dark lines. We see some lines that are wide, some lines that are very narrow, some lines that are close together, and they're all at a very specific color. So this gives us even more information. This tells us a lot of different things. So if we look at the different categories, the different types of stars, we can kind of group them by a pattern. So we notice a bunch of stars that have lines here and not too many dark lines over here. We call those O stars. And then we notice another pattern. They still have these lines, but they're starting to get a little darker lines over here. And then A has even darker lines. These stars have more complex spectra with more and more lines in there. So what we're learning from this, we've got a couple different things. if we take hydrogen gas in the lab and we heat it up, we see a dark line here, and a dark line there. And what's happening is the hydrogen electrons are absorbing those wavelengths of light. They're just the right energy to kick that electron up to the next orbit. And so we can identify that in these stars, their outer atmosphere is mostly just hydrogen. Then we can say, well, these ones down here, they have more lines. They have hydrogen plus some other things in their atmosphere. And boy, these stars down here, they got everything. They've got titanium oxide, sodium, titanium oxide again, ionized calcium, and all sorts of other elements in their atmosphere. So we can categorize our stars by types. And we call them O, B, A, G, F, K, M, and a few other letters. So this category scheme was invented by Annie Jump Cannon, who was one of the Harvard women who started this area in astrophysics. And her team's job was to categorize stars, their spectrum, and sort them so that we can learn more about them. They did 350,000 stars and more into these categories, and we could see patterns. So one thing that we could see are these categories, but then we also could get more information out of this spectrum. Because the spectrum is not just what we see in visible light, it is this whole range of wavelengths. So infrared is visible light, and the red is just a little redder. The wavelengths are a little different. Our eyes do not see them, but it is still light. It still carries the same information about the elements that are in that gas. We go from gamma rays, X-rays, ultraviolet, infrared, microwave. We do a lot of radio astronomy. Radio waves turn out to be very, very useful wavelength to observe in because the gas that's in galaxies can glow in radio. And so we can get a lot of information there. And so this is one more way of observing the sun. And this is that, is this the right one? Yes. So this is at Solar Dynamics Observatory. It's been observing the sun for many years. It has lots of cameras on it. And so these are observations all in different wavelengths. And each wavelength tells us something different. So the same spot looks different in these different wavelengths and tells us about the processes that are happening at that place. So there's a sunspot. You can see the magnetic field in certain wavelengths and not in others. So this is another way that we can gather data, is looking at the different wavelengths at the star. I'm going to pause it because it's hypnotic, but I don't think you want to be here until 9 o'clock. All right, so in addition to identifying elements based on the rainbow spectrum, we can identify temperature based on the spectrum. So in the lab, if we take a gas and we heat it up, we notice that it emits more light at particular wavelengths, which is a particular color. And so you've seen this on your stove, right? You turn on your stove, it starts out black, and then it turns red, and then it turns bright red. And then if your element overheats, it turns yellow, and then it probably catches on fire. But you've probably seen videos of this happening with a poker. It eventually turns white hot. Well, white is a combination of all the colors. So that thing is glowing in all these different colors. So we see the same thing in the stars. So stars that glow more brightly in the blue are hotter, 15,000 Kelvin on the outside surface. Stars like our sun that glow brightest in the yellow are cooler, And then stars that glow brightest in the red are even cooler than that, about 30,000 Kelvin. So if we look at the stars by looking at their color, we can judge their temperature. So a bluer star is hotter, a redder star is cooler. And we use this data to find patterns. So we're looking for information that might tell us more about why are some stars different than others. And if we make a plot, we call this the periodic table of stars. The Hertzsprung-Russell diagram is the official name. But if we plot temperature across here, so this is cool, low temperature, red. This is hot, blue. This is the brightness, or how bright the star shines, which we can measure separately, adding up its brightness over all the wavelengths. We see a pattern where if we take a whole bunch of stars and put them on here, temperature versus overall brightness, we see a lot of stars in this line that we call the main sequence, including the sun. We see a group of stars here that we call giants. We see a group of stars up here that we call supergiants. And then we see a group of dim, hot stars called white dwarfs. And so the next question is, does this mean anything? And how does the position on this graph, what does it tell us about that star? And so we'll see that here in a minute. So then the question is, we just said the sun's, what, 5 billion years old? About 10 billion years total, it'll run out of fusion energy. How can we figure that out? We've been doing science good for about 1,000 years, right? Been doing science bad for a couple thousand years. Well, not as good, it's not necessarily bad, just not as precise. But that's just a tiny fraction of these stellar lifetimes. We don't watch a star get old. We just see it in a fraction of a second. So the problem is equivalent to if an alien came to the Earth and took a picture of the whole Earth 1 second and then left, and then tried to figure us out. What would they do, right? So let's look at this picture. Really weird picture. I don't remember where I got it. I don't know why they're holding these trophies, but.
They showed up.
All right, so 1 second picture. What do we know about these things called humans? Can we sort them by age? I want to know which one's young, which one's old. Well, I'm going to start sorting them by height, right? Young, short, tall, old. Does that work exactly? No. Is it a good first approximation? Kind of. I'll never grow old because I'm not very tall. Good thing. But as a first approximation, tall, short, young, tall, old is not too bad. If we add in other details like hair color, which we can't see in a black and white picture, wrinkles on the face, those are things we can observe and sort people more closely in age. Is it 100%? No, some people go gray early, some people dye their hair, so it's not gray at all. Some people have wrinkles, some people have plastic surgeries, you know, so we always have these aberrant people. Same like we have some stars that don't quite fit, but in general we can get a pretty good idea by saying, I think these stars are younger and these are middle-aged and these are older, and if I've got billions of them to work with. If I line them all up, they make a pretty good progression. And it fits with the science. And so this is what we do. We get a fraction of a second of a billion stars, and we try to figure out their total life cycle, because we can't watch it. So this is the theory. This is our most well-substantiated theory of star formation. That we start with a large cloud of dust and gas, of which we see many in our universe. And that gas cloud begins to contract from some sort of event, perhaps a nearby supernova or some stars passing through it. This is on a stellar scale, so it can happen really slowly. It starts to contract. And as it starts to contract, it starts to spin a little bit. And then it starts to contract and it spins faster and starts to contract and spin faster. And eventually the center becomes very dense, very hot, and can start to glow. So at about 1,000 degrees, do you care about the units at 1,000 degrees? Celsius, Fahrenheit, Kelvin, it's all 1,000 degrees. Or million degrees, sorry. Million degrees, doesn't matter the units, it's actually Kelvin. But so 1,000,000 degrees, the star starts shining. It is not undergoing fusion, but it is hot from gravitational contraction, and it's glowing. If it continues to contract, it will eventually heat up even farther. And when we get about 10 million degrees Kelvin, fusion will begin in the center. And as soon as we have fusion in a star, we call it a star instead of a protostar. And as soon as we have fusion, that star changes, and it starts to blow off the atmosphere and blow the gas out of the solar system, and then it becomes something similar to what we have now, with the gas driven away from the star. So if this is our theory of star formation, there's millions and billions of stars just in the Milky Way. We expect to see some out there at each of these stages, right? So if we look out there, we do. So this is the Orion's Nebula. This is all dust. This is a clump of more dense dust that's glowing. That's why it's brighter than the background. It has an area in here where it looks like there might be a little extra light. Maybe we have a protostar in there. And if we look at the size scale, this is the orbit of Neptune. So it's about the right size to be a forming star and eventually a solar system. We see other things called protoplanetary disks where we have a brighter background. We have a dark area and then a light area in the center. What's happening here is you have a glowing dust cloud behind this disk. You have a very dense disk that's now blocking the light. It's so dense. So think of a really thick fog. And then on the inside is your star that's almost ready to start fusion. It's glowing very brightly. If we measure the temperature of that glow, we'll find it's around that protostar temperature that we expect. So we do see evidence, lots of evidence for these protoplanetary systems where we're forming stars. If we then talk about what happens next after our star is born, the life cycle of a star takes two paths. It can go on a low mass star path, or it can go on the life cycle of a high mass star, and what happens to them is different. So we'll first talk about low mass star. This is like our sun. So when you have fusion, you start out on the main sequence here. Up here, we'll find out our higher mass stars, so if they're bigger than the sun to start with. And these are lower mass stars that are smaller than the sun to start with. Then it will undergo fusion for about 10 billion years. And when it's doing fusion, it's not the whole star that's undergoing fusion. It's the core, the center of the star, that has enough pressure and enough temperature to ignite fusion. The rest of the star out here is hot. This layer right here is undergoing convection. Convection on your stovetop is boiling, right? So this star is boiling. We've got hydrogen gas on the bottom that heats up and rises, comes out to the outer edge, cools off and sinks, and we get the star that's actually, the surface is boiling. NASA has some really good video of these convection zones. I just don't have it linked in here. After about 10 billion years, that center area of fusion hydrogen, it starts to run out of hydrogen. It has nothing left to fuse for the hydrogen sequence. And so as that fusion slows down, the outward pressure of the energy flowing outward is disturbed, and the inward pressure of the mass of the sun falling, being pulled in by gravity is not in balance anymore. So two things happen. The center begins to contract, and the outer edge begins to expand. And so as this happens, the star becomes a red giant. Now, the center might contract enough to have helium in there and not undergo fusion. It's a little bit bigger that helium will fuse, but we'll talk about that in the next stage. We can also have just a shell on the outside of the helium that's hot enough to make fusion in a layer like an onion, where there's no fusion in the middle, just really hot helium, and then the outside there's a layer of fusing hydrogen to make more helium. Now, this expands. It expands a lot, but how do we visualize what a lot means, right? So to give you a sense of scale, we've got Mercury, Mars, Venus, and yes, Mars is really small. That's why it doesn't have its atmosphere anymore. It doesn't have enough gravity to hold on to it. Earth. Then we take Earth and we shrink it down to this size. We have Uranus, Neptune, Saturn, Jupiter. We take Jupiter and we shrink it down to this size. We have our sun. Oh no, that's WOOF 439, which is a very small star. Our sun. So there's Jupiter. Earth is about a pixel on that picture. And then this is Sirius, which is a larger star like our sun. We take Sirius and we shrink it down to here. We have Pollux, Arcturus, and Aldebaran. This is a red giant. So our sun goes from, so imagine this sitting next to there, to this size when fusion stops. Helium or hydrogen fusion stops. So it grows a lot. Now, if there's enough mass, then that core will heat up even more, and we'll start to get helium fusion in the center. And when we get helium fusion, it is rather dramatic, because as soon as you start to get helium fusion, you get a chain reaction. And within a matter of seconds, the whole core is fusing helium, and the core has expanded. And it's releasing a ton of energy, which has rather dramatic effects on the outside of the star. If we just talk about helium fusion, there's only enough helium in this model for about 0.1 billion years. So 10 billion years of hydrogen fusion plus 0.1 of helium fusion, very short life cycle, very short stage of this life cycle. So once that helium runs out, our balance is blown up again. It's imbalanced. And the outer layers of the star are blown off. And the only thing that's left is that center core, which we call a white dwarf. It is that helium with a couple of layers on top of it. Very small. And we have this giant nebula around the outside, which can then be used for forming another star. So if we look at our Hertzsprung-Russell diagram, so here's our brightness and our temperature. Here's our sun. When it goes into the supergiant stage, it will get the outer edge of the sun, the part we can see, will get cooler, but it'll expand and so it'll get brighter. It will live up here a very short time period until it runs out of fuel and it blows its outer nebula off, and then it comes down here and it's a white dwarf. So when we look at these stars and we have a photograph of a bunch of stars on the Hertzsprung-Russell diagram, these are stars that are dying. In a very short time period, they will not be doing fusion anymore, and they'll be down here in the white dwarf stage. So these are dead stars. These are dying stars, and these are ones that are still alive. So if we look for evidence of this, we can look at something called a globular cluster, which is on the outer edge of a galaxy. They are about 1 million stars that all formed at the same time. They're isolated from everything else. They have no gas. They can't make any new stars. They're all the same age. And if we plot them all on a Hertzsprung-Russell diagram, we see this shape. We see no main sequence branch up there. All the high mass stars have run through their life cycle. And we can show in the science and the math that if you have more mass, all of these life cycle sequences are shorter. So you have a shorter time of burning helium because you burn it too fast, and then you die. So these stars here are just starting to not be able to fuse helium or hydrogen anymore. These up here are doing helium fusion, but very soon they'll be nebula and turn into old white dwarfs down here. And we can look at dozens of globular clusters, and they all have this shape. If we look at young clusters, then there aren't any of the old stars. There aren't any of the white dwarfs in there. We can also look for evidence of the nebula being thrown off from these stars, and so we can see lots. You've seen a million of these pretty pictures out there, right? So these are stars that have run out of fusion energy inside their core, and they have blown their outer atmospheres off. So what'll happen to the Earth? We said the sun get really big, right?
Coming from the deep, cold reaches of the solar system, flying in toward the sun, passing the orbits of Neptune and the binary pair Pluto and Charon. We are seeing our home system as it may look about 5 billion years from now. Looking closely, we see that something's gone dramatically wrong with the sun. Its fuel supply running low, our star now swells in size, becoming a red giant, engulfing the orbits of Mercury, Venus, and our Earth. The sun now goes unstable and puffs off shells of plasma and gas, eventually hurling outwards the components of what will become an immense fluorescent nebula for all the galaxy to see. What remains of the sun now shrinks down to become a dense, cold white dwarf star, the lonely cinder of the former planet Mars as its closest companion.
So depressing. But when is that going to happen? 5 billion years. Are we going to be here? Probably not. Yeah, so we got a while. All right, so what about high mass stars? Well, high mass stars use their fuel faster. They burn hotter. They have more to start with, but they use it so much faster. They have a much shorter lifetime in all of the stages. So it will go through similar stages of hydrogen fusion, and then hydrogen shell fusion, and then helium fusion in the center. And it goes through that expansion and contraction. But then after that, it's massive enough that its center can get hot enough to do more fusion. So right before the end of the star, the inner layers look like an onion. So on the outer layer, we have just hydrogen, part of the star that's not hot enough for fusion. But then we have hydrogen fusion in a layer, helium fusion in a layer, carbon undergoing another fusion reaction in a layer, oxygen, neon, silicon, magnesium, all in layers around iron in the center of the star. So we get this onion level of fusion that's generating a lot of energy for this star. So what we see on the Hertzsprung-Russell diagram, like these are the high mass stars up here. They move back and forth in the temperature range. So they go hydrogen, helium, carbon, then the next one, then the next one. And so they move back and forth as they're going through these different stages. But they're up here. They're very bright, very large, very hot, for the most part, stars. And we call those supergiant because they get even larger than the giant star. And so this gives you another view just how big these supergiant stars are. So each time it moves, it's going to shrink to give us a sense of scale. So there's the Earth's over there. So this is the size of our star will be when it ends its life in the red giant area. Yeah. These are really difficult to visualize how large these stars are. Now, what constellation is this? Oh, I have it shown up there. Orion, right? Get the belt and the sword and the hips and the shoulders and the head, depending on how you draw it. So Betelgeuse is a red supergiant. So it is a high mass star at the end of its lifetime, currently very large, very bright. If you look at Orion on a clear night outside of the city, you can see Betelgeuse is red, and this is Rigel, another supergiant, and it's blue. So these are some of the easiest stars that you can tell that they're actually a color and not just white, because they're very bright. It's getting to be winter, so this Orion will be up in the evenings if you want to go look for it in the south. All right, so why is there iron in the middle, and why do we stop at iron? The nucleus of iron is special in that how it's configured, you cannot do fusion and get energy out of it. You put energy into it to get the next heavier element. And so fusion as a natural ongoing process stops at iron. And so the inside of this star builds up a giant ball of iron. As it begins to consume the fuel in these outer regions, it will start to not have enough to undergo fusion. And gravity will start pulling in as if fusion isn't pushing out quite as much, and will disturb that balance again. So what happens is eventually that iron core gets dense enough with enough pressure on it that it collapses. And at this point, it's about the mass of the sun in a space the size of the Earth, full of iron. And then it collapses, and it shrinks into a ball just a few miles across, composed only of neutrons. And it happens in a fraction of a second. So think of this as an atomic nucleus that's only neutrons. Those neutrons are that close together. What do you think happens? What are stars known for? They go supernova. Yep. So this releases a lot of energy. We finally have enough energy to go past iron. And we get all the elements, all the other elements. So it's a review of chemistry, periodic table, right? So the Big Bang made hydrogen and helium. Pretty much that was it. Then stars, like our sun, make more helium with hydrogen fusion. If it's a massive enough star, it starts to make carbon. Then high mass stars make these elements in those onion layers. And so we have a higher proportion of these elements in the universe because more stars are making them in their cores. So where do all the others come from? Supernova. So the gold in your ring came from a supernova, which is cool, right? The carbon could have been made inside of a star. That's still cool. It's carbon in your diamond, right? All right, so supernovas are very dramatic. They throw off all the outside of the star. Sometimes they end up with a black hole in the middle, which we'd have to have another lecture for that. What is the observation evidence of this? Have we ever seen supernova? Yep, every year, all the time, we see them. There's billions of stars out there. We've got great telescopes. We see supernova happening all the time. 1987, this star went supernova. This was visible to the naked eye. I was too little to think that was cool. I don't remember it at all. Were you guys born in 87? No. Don't tell me that. We can also watch this gas cloud from supernova being thrown off. We can watch it happen if the star is close enough. So this star, Monocerotis, maybe, in 2002, started throwing off a nebula. May, September, October, December. In 6 months, we see a big change. Now, the sense of scale, this is like bigger than the solar system. This is moving fast and is giant. But we can see it because we have great telescopes. This happened to be relatively close, so we could take a good picture of it. So we've seen this happen. We have lots of evidence that support these hypotheses. All right, so in the big picture, where do stars form? Well, our galaxy is the Milky Way. It is a spiral galaxy. This is an artist's picture. Right? If you're inside something, you can't get a bird's eye view if it's the size of a galaxy. So this is an artist's picture of what we think the solar system looks like. In the center, there's a bulge of older stars. On the outer edges, there's a kind of a pancake with spiral arms. And we are in this region. These are the globular clusters, the original older stars that we use to support some of our theory here. If we take a side view artist rendering, the galaxy is actually very thin if you're a spiral galaxy. You have a bulge in the middle. We have this disk, and it is formed of younger stars and lots of gas. We're about here. We're 28,000 light years from the center. We're moving about 220 kilometers per second, the sun is, taking us with it, which takes us about 230 million years to go once around the galaxy. So we haven't orbited very often. Where stars form in a spiral galaxy is typically along these spiral arms. So this is a real photograph. This is another galaxy. The bulge is here. We're looking down on the pancake. We see two spiral arms. The dark are the dense gas that's blocking the light from behind it. If we look along there, we see lots of glowing stars. We see blue and red. The red are the older stars, and the blue are the younger stars. And so right along this gas lane, we see clusters of all these stars forming in these other galaxies. And that's right where we think they would form. There's not as many in here, and these tend to be older stars where there's not the gas. So when we look at the universe, we see billions of galaxies. Each galaxy has billions of stars, and all these galaxies are different. So we have irregular looking galaxies. We have elliptical galaxies that are like a ball of stars. And then we have lots of spiral galaxies. This is the Hubble Deep Field over here. Each item in here is a galaxy. It's not just a star. Each one of those is a galaxy with billions of stars in it. So I wanted to conclude with Psalm 19. The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge. They have no speech. They use no words. No sound is heard from them. Yet their voice goes out into all the earth, their words to the ends of the world. So, questions? Thank you. Yes?
In the globular cluster HR diagram you showed, why aren't there any sort of intermediates between the giants and the white dwarfs? You know, if they're going through that whole cycle, is it just they're real rare and so you just don't likely find them?
Yeah, it's
So why don't I see the path?
Why don't you see the path along here?
Yeah, exactly.
It happens so quickly that we don't see very many there. So exactly what you're thinking. So the stars spend 10 billion years here. It's easy to catch them at that moment in time. They spend 0.1 billion years in this region. And then the moments that they're throwing, they go from helium to throwing off their atmosphere, and having this left over is just a fraction of that. So it's down in 10 million years, if I remember right.
But in all the globular clusters, do you see any in some of these?
I imagine there's probably some over there. This particular one doesn't have it, yeah. Yes?
Earlier when you were talking about the death of a low mass star, it the dust and stuff, it explodes everywhere, and the core stays there so that another star can be created. My question is, can a high mass star be created from that core?
No. So the core that's left over are these white dwarf stars. So these stars are about the size of the Earth, not too much larger than that. They're very, very, very hot, but they're not doing any fusion, so they're just cooling. The gas that's thrown off in the outer ring could make another star, but it has less mass than it started with. And so the mass, if you took all of that back and made another star, it would be smaller. And so high mass stars can give birth to smaller low mass stars eventually. Typically though, what happens is you have a giant gas cloud to start with and you get a whole bunch of stars in there and they mix it all up. So something related to that point, if we go back to this star classification pattern, these stars only have hydrogen in their atmosphere. They are the older stars that are formed from original Big Bang gas of hydrogen and helium. These stars have other elements, sodium, titanium. Titanium came from a supernova. So this star was born out of the remnants of a supernova. So it began its life later in the universe, or in a place where somebody else had already been born and died. Yes?
Does the theory of the lifespan of stars change whether or not we have a young Earth theory or the older theory? Do some of the star theories perhaps change or fall apart under the young Earth theory?
Yes. So in the young Earth theory, none of this science supports the young Earth theory. All of the theory of the formation of stars and planets requires billions of years to get to a planet that has an atmosphere that can support life. Yes?
Now, given the time that it takes for light to travel, when we say we are seeing this or we're seeing that, what we are really seeing is something that happened a long time ago.
Yes, exactly. So when we look at a star that's 630 light years away, we're looking 630 light years, or 630 years in the past. So 630 years ago, that light started coming from the star to us. Now within our Milky Way, that time lag is not that significant in the lifetime of a star. We're talking 100,000 years for light to travel from one side to the other versus 5 billion years that a star is old. But when we start looking at galaxies that are very far away, we do get galaxies that are way, way, way back in the past, billions of years ago. And so we can look back in time, and we do see differences in galaxies in the very early universe. There are fewer of these older stars with more complex spectrum. Yes?
So which of these are real pictures and which are artists' pictures? This always confuses me.
I know. This one's artist.
Okay.
So I tried to pull as many real pictures as possible into this, but some of them were illustrations. So.
Okay.
But even the real pictures are sometimes enhanced or colorized. Or
yeah, so if we go back to this picture back here, if this was real in radio, we wouldn't see it, right? Our eyes don't see radio.
But would we hear it?
No.
This is a radio wave. Was it
not
playing rock and roll?
No, it's not a sound wave. No. So, yeah, so this is, interpreted. This one is infrared, so they have colorized it into something that we can see. This is another infrared, colorized. When we look at the nebula, they do even more to it. So let me see if I can find this one. This, if you look at it in a telescope, does not look red and purple and orange. These are colorized for the elements that are there. So they're looking at one particular wavelength that hydrogen shines brightly at this temperature and saying, oh, this one's a hydrogen. I'm gonna make it, I don't know, purple. I don't know what the colors mean on here. But then this one's helium. It's shining at this other wavelength, so I'm gonna colorize it and look at this one. So it's real, but it's interpreted kind of, so that we can see it. All right, other questions? Yes?
Do scientists have a have an idea for the rates at which stars are being born and dying?
Yes, it depends on the region. So in our Milky Way, along the spiral arms, stars are currently being formed and dying at a rapid rate. I don't know what it is. In the center core of our galaxy, stars are not being born anymore. There's not any gas there. It has been either used up or the radiation pressure from all the stars in the core has pushed it out. Old galaxies sometimes have very few areas of gas, and then you can't make new stars. You had a question? Yes.
The bulge at the center of our galaxy, what's it made out of?
Older stars in a black hole, really big one. So there's a black hole in the center, and then there's a really big bulge of older stars that formed earlier in the process as the gas was still collecting into the disk. And so we have younger stars in the disk. Yeah.
So this one that you told us is colorized. What do you actually see through a telescope? What would this look like?
If you looked in a visual wavelength telescope, you would see a white, fuzzy shape. There's some nebula that in a normal telescope like the one we have, you can see that would look like a disk. There's what's called a ring nebula that looks like a smoke ring, just like a smoke ring. I mean, it's white and then it's kind of dark in the center. If you take a photograph, you can sometimes get color out of it. But our eyes don't collect photons fast enough for us to see the color. So there's a very few red coming in, there's very few blue coming in. Our eyes just see kind of black and white for the most part, unless there's a lot of red coming in. But a photograph, a long exposure photograph, that's where we get the colors.
Well, let's thank Dr. Coy once again.